Hello, my name is Christina Psaroudaki and I currently work in Caltech. I would like to thank the organizing committee for giving me the opportunity to share my work on Skyrmions. The title is Spin Wave Radiation by Topological Charged Dipole and is in collaboration with Sebastian Diaz, Tomoki Hirosawa and Daniel Laws, and is about how an interacting Skyrmion and Skyrmion pair can be thought of as a topological charged dipole and what kind of signatures are produced in the emitted spin waves. When we talk about topological charges in 2D materials, we refer to Skyrmions, stable magnetization textures characterized by a finite topological charge. Their dynamics is governed by topology. That gives rise to very interesting phenomena, including the experimental observation of the Skyrmion Hall effect, in which Skyrmions are deflected in a direction transverse to the applied force, the topological Hall effect in charge transport, and the suggestion of the existence of topologically protected chiral magnonic edge states in Skyrmion crystals. In reality, the Skyrmion family is very large, so the magnetization texture is determined by the form of the Dialonczewski-Morilla interaction, which is in turn dictated by the crystal symmetry. Famous examples are a Bloch Skyrmion in materials with a cubic symmetry, or a Snell Skyrmion in thin films with interfacial DMI interaction, while the existence of textures with an opposite topological charge, anti-Skyrmions, have been suggested for materials with C2V symmetry and experimentally observed in Heusler compounds with D2D symmetry. The spin wave spectrum around a Skyrmion is consisted by the usual propagating spin waves with this quadratic dispersion above a gap, although a number of localized bound states exist below the Magnon gap and correspond to Skyrmion deformations. Of particular importance for our work is this counterclockwise mode with an energy exactly at the gap, which corresponds to a rotation of the out-of-plane spin component around the Skyrmion core. And by an analytical and numerical calculations, we observe that the sense of gyration of these modes depends on the sign of the topological charge. So in particular for this mode, we identify that it will correspond to a clockwise mode for an anti-Skyrmion. It is also known that these modes are activated by microwave fields. For example, an out-of-plane microwave field will activate the breathing mode, while in-plane microwave fields activate these gyration modes. Both of these modes have been experimentally measured in Skyrmion hosting ferromagnetic insulator in the gigahertz regime. It is kind of well known that we can manipulate Skyrmions by Magnons. One example would be the unidirectional Skyrmion rotation induced by the rotational flow of Magnons under the application of a thermal gradient, and we have also suggested that Magnons under microwave fields can result a unidirectional propagation of Skyrmions along a nanowire. And there are a few of nice reviews on the topic. Here in this work, we suggest quite the opposite, how the properties of the emitted spin waves can be controlled by the topology of the emitter, which is the Skyrmion core. With respect to dynamics, Skyrmions and anti-Skyrmions having opposite topological charges will have opposite lateral deviations with respect to the Skyrmion Hall effect, but when they are realized in bilayers, the interacting Skyrmion and Skyrmion pair with a vanishing topological charge will lead to the absence of the Skyrmion Hall effect. And as I said before, in-plane microwave fields will activate the counterclockwise mode for the Skyrmion and the clockwise mode for the anti-Skyrmion of the same size. So now, inspired by this simple concept of a charged dipole radiation produced by a pair of opposite charges, we would like to explore whether a spin wave dipole radiation can be emitted by a pair of opposite topological charges. The basis for this realization is a bilayer of magnetic materials hosting a Skyrmion and an anti-Skyrmion, while the two layers are coupled through a ferromagnetic interaction, and the whole system is under the application of an in-plane magnetic field that will activate the gyrotropic rotation of the core. To simulate the magnetization dynamics, we solve the LLG equation with the frequency chosen to be on resonance with the gyrotropic modes, and keep track of the dynamics of the spin waves, which are defined as the Z component of magnetization above the ferromagnetic background. We also focus on the dynamics of the particle center of mass, defined by this equation, and in particular on the dynamics of the charge separation distance. And we note that the excited spin waves, they do represent collective modes of the bilayer, so they propagate from the source to the edge of the sample with characteristics that are related to the bilayer. For a pair of opposite charges, both the skyrmion and the anti-skyrmion will perform elliptical paths, as you can see here, with opposite sense of gyration, while the charge separation distance oscillates back and forth and along this line obtained by this angle psi. The second prominent feature is the directionality of the emitted spin waves that you can see here, with a preferred radiation direction that coincides with this angle psi. This configuration clearly corresponds to topological charged dipole with the directional spin waves, and this is further supported by the radiation pattern, defined simply by the time average Fourier transform, which presents the characteristic two-source dipole feature. To get an understanding of the origin of this angle psi, we now try different pairs of helicity, and we conclude that the preferred radiation depends on the helicity of the charged dipole and can be used to manipulate the propagation of the spin waves. Perhaps the least interesting type is having two textures with the same charge and helicity that will perform identical paths with a vanishing charge separation distance. In this case, the emitted spin waves, they exhibit symmetric radiation patterns as a result of a single monopole emitter. Just to understand the difference between those two types and identify the signatures of the charge interaction in the radiation field, we now study the far-field spin wave amplitude as a function of the interlayer coupling. For a bilayer of opposite charges, the amplitude grows linearly, indicating that the source is indeed an interacting charged dipole and that the interlayer coupling could be an excellent mechanism to tune the amplitude. For a pair of the same charges, the amplitude shows a very weak dependence, suggesting that even when the layers interact, the spin waves remain unaffected. In addition, the amplitude can be enhanced by tuning the ratio of the Dialonczewski-Morilla interaction over the exchange interaction. So we observe that the amplitude is increased when d over j is decreased. For typical units, the emitted spin waves have short wavelengths in the sub-100 meter regime due to the nanoscale of the Skyrmion core. Turning now to bilayers consisting of textures with the same topological charge but different helicity, although the two particles will have the same gyrotropic mode, a null Skyrmion performs a larger circular path compared to a Bloch texture, while their charge separation distance follows this circular path with a sense of gyration that is determined by the topological charge. So spiral outwards traveling spin waves are created in Skyrmion bilayers, while anti-spirals in anti-Skyrmion layers. So finally, we would like to analyze the dispersion relation as a function of the excitation frequency. So to do that, we focus on the radiation patterns. First, we note that on resonance, there is a distinct short wavelength mode, indicated here by this red rhombus, with a corresponding intensity that vanishes as we go away from the resonant frequency, and that happens for all bilayer types. This is the short wavelength mode that is activated by the gyrotropic motion of the particle core, and is further enhanced by the bilayer coupling with properties that can be linked to the topology of the emitter. On top of this mode, we also identify a long wavelength mode, indicated here by this yellow circle. That is the usual spin wave mode expected for the ferromagnetic bilayer, with a quadratic dispersion plotted here. We see here the evolution of these two modes as we increase the frequency. So the short wavelength mode loses its intensity, while the long wavelength mode will dominate over the Magnon spectrum. Just to make contact with efforts on spin wave radiation, we note that directional spin waves can be created in arrays of spin torque nano oscillators as the result of interference patterns. Spiral spin waves have been suggested to exist in metallic spin-hole oscillators in the limit of very large amplitude of the Dialno-Ziskin-Maria interaction and very large applied charge currents. While conceptually closer to our work is the experimental observation of spiraling spin waves in a stack of dynamically excited vortex cores, with the spin wave propagation imaged by time-resolved scanning transmission X-ray microscopy. In particular, we suggest that there are no experimental barriers to realize our proposed system, so the spin wave generation can be realized in a large variety of Skyrmion hosting materials, including magnetic insulators, in a stack of two materials separated by a spacer using current technology. Of course, a crucial step is to ensure that the Skyrmion and anti-Skyrmion are approximately on top of each other by either utilizing a confined geometry such as a nanodisk, or we can use engineer pinning defects for a precise positioning. So to summarize, we suggest the formation of a topological charged dipoles using Skyrmion and anti-Skyrmion bilayers in which act as a spin wave emitter of directional radiation with clear dipole signatures. The proposed spin wave generation mechanism is reliable and robust and in the sub-100 nanometer wavelength due to the nanoscale of the Skyrmion core. And the characteristics of the emitted spin waves, since they are linked to the topology of the source, allows a control of the spin wave features, including, as we suggested, the amplitude, the preferred radiation, the direction of propagation, and the wavelength. So at this point, I would like to thank my collaborators and the funding agencies, and I would be happy to accept your questions.